plus k sigma, you can find a lower bound for the probability that x is less than mu plus k sigma, and that'll namely be 1 minus mu over mu plus k sigma. Today we're going to finish section 3.3. We'll review student comments, we'll prove Chebyshev's inequality, we'll see another formula for variance, we'll look at properties of variance, and we'll briefly discuss the central limit theorem. So remember the concept test from last time. A list of non-negative numbers has an average of 1 and an SD of 2. Let P be the proportion of numbers over 5. To get an upper bound of P, you would need to use Markov's inequality, but not always for the reasons that some of you said. So one person said C can't use Markov because the data falls below 0. No, I wrote that the data is in fact non-negative numbers. So you can use Markov. One person said it's B because we're only interested in the right tail region. Well, that's not a reason why you're using Markov. You'd want to compare Markov and Chebyshev. Chebyshev can also be used to just find the an upper bound for the right tail region, as I showed you above. So a person correctly responds that it's B because the Markov gives a smaller upper bound in comparison to Chebyshev. 1/5 is a tighter upper bound than 1/4. So one person says you can't be 2 SDs below, so Chebyshev doesn't work. That is not correct. It's true you can't be 2 SDs below because these are non-negative numbers, but Chebyshev can still apply to find the upper tail. So let's go over the proof of Chebyshev. This really follows from Markov's inequality. So Markov says the probability that y is greater than or equal to a is less than or equal to the expectation of y over a, where y is non-negative and a is positive. So it involves a smart choice of y and a. So we're going to let y be the squared deviation from the mean, which is non-negative, and we're going to let a be k times the SD of x squared. And so then by Markov's inequality, we get that this probability is less than or equal to the expectation of y, which is expectation of x minus expectation of x quantity squared, which is just the variance of x by definition. And the denominator is ksdx squared, which is k squared variance of x. So the variance of x cancels, yahoo, and you get the 1 over k squared, so we're almost there. So we can take the square root of both sides of the inequality inside the probability. So remember that square root is a increasing function, and so if a is greater than b, then the square root of a will be greater than the square root of b. So that's just the way that works. So you actually have equivalence here because x minus expectation of x squared that's that. And then when we take the square root, that is just the absolute value of x minus expectation of x, which is just the definition of what absolute value is. And then the square root of ksdx squared is the absolute value of ksdx, but ksdx is positive, right? Because SD is always positive. So there is Chebyshev's inequality. So on to another formula for the variance. So remember, property of expectation constants pull out. So in particular, the expectation of x is a constant. So if you see expectation of xx, that is just the expectation of x pulls out, so that would be expectation of x, expectation of x. So what we're going to do is, to make an alternate form of variance, we're going to FOIL the x minus expectation of x squared, and so you get x squared minus 2 expectation of x plus expectation of x squared. So now you distribute the expectation, so we get expectation of x squared minus, now we pull out the 2 expectation of x, because that's a constant, so we get 2 expectation of x, expectation of x, and then plus expectation of x squared, because that's just a constant squared. So then we have minus 2 expectation of x squared plus expectation of x squared is just minus expectation of x squared. So that gives us this alternate formula for variance, and hence a formula for what the expectation of x squared is in terms of variance and the mean. That's very useful. So for example, let x be a non-negative random variable such that the expectation of x is 100 and the variance of, and that's also the variance of x. Can you find expectation of x squared exactly? So of course you can use this formula to do that, since you know the variance of x and the mean. Furthermore, can you find the probability that 70 squared is less than x squared is less than 130 squared exactly? If not, what can you say? So, well, we can't do it exactly, but we could do it with Chebyshev. So we don't know what the SD of x squared is, but the probability, but 70 squared is less than x squared is less than 130 squared exactly when 70 is less than the absolute value of x is less than 130, and the absolute value of x is just x, since x is non-negative. So, so the probability that we're looking for is just equal to the probability that x is between 70 and 130. And that is, we know how to find the probability of the tails using Chebyshev. Here k is 3, so that's less than or equal to 1 over 9. So we can get a lower bound then for the probability that we're between 70 and 130, namely 1 minus 1/9, which is 0.89. Note that you could use Markov to do this as I've written here, but you're not going to get as good of a lower bound. So better stick with Chebyshev in this case. But you would need to check both, I suppose. We did a concept test. X is a random variable with expectation x is 3 and SD of x is 2. True, false, or maybe. Probability that x squared is greater than or equal to 40 is less than or equal to 1/3. So we can apply Markov here once you realize that we know the expectation of x squared is 13. And so by Markov, we get that it is less than or equal to 1/3. Just to note that you can't use Chebyshev here because x isn't necessarily non-negative. And so when you take the square root of both sides, when you take the square root of both sides, the square root of x squared is the absolute value of x, and that's not necessarily equal to x. So properties of variance. So the main property is that, let's look at standard deviation for a minute. We know that standard deviation is the average spread, right? So, so clearly the spread in for x, as shown, is 1/3 as large as the spread of 3x. You can just see that in the picture. The spread is 3 times bigger. And then when you take minus 3x plus 1, that just flips it over the y-axis and translates it so by 1. So that doesn't change the spread at all. So the effect of transforming your random variable x into, let's say, ax plus b For the SD, that's just the absolute value of A times SDX. So in the example above, the effect was the SD of minus 3x plus 1 is just 3 times the SD of x. And variance is just the square of SD. So variance of ax plus b is just a squared variance of x. So just remember that constants pull out a variance as a square, and constants that are multiplied by times x, and just constants by themselves die under variance. So we have this important result that the variance of x plus y is the variance of x plus the variance of y if x and y are independent. So we can see that's true for when x and y are independent binomials, because we know that x plus y is binomial n plus mp, and the variance of x plus y is then n plus m times pq, which is n times pq plus m times pq, which is the variance of x plus the variance of y. So it's confirmed there, and furthermore, we see that we do need independence. So if x is the number of hours a student is awake during a day and y is the number of hours a student's asleep during the day, then x plus y is 24, and the variance of x plus y is in the variance of 24, which is 0, which is not the variance of x plus the variance of y. So the variance formula will need to be for independent x. So then we did an example here where x1, x2, x3, x4 are lengths of independent calls on a telephone, with expectation 6 minutes and SD 7 minutes. T is the sum of the length of the 4 calls. Give a lower bound for the probability that T is less than 60. So we know how to find an upper bound for T, probability that T is greater than or equal to 60, using both Markov and Chebyshev. So we can do that. We just need to figure out what the expectation in an SD of T is, which we see that the expectation is 24 and the SD is 14. So you can see that an upper bound for the probability that T is greater than or equal to 60 is 0.4. So the probability that T is less than 60 has a lower bound of 1 minus 0.4 or 0.6. Furthermore, 60 you can write as 24 plus 2.57 times 14. So we know that k is 2.57, and so an upper bound for probability that T is greater than or equal to 60 is 0.15, and so a lower bound for probability that T is less than 60 would be 1 minus 0.15 or 0.85. Finally, central limit theorem. I'm just going to illustrate this with an example, and we'll talk more about this at a later time. Let x1 to x2 and so on be IID Poisson. Say that so it's up to 10. So let S sub 10 be x1 up to x10. So we want to find the probability that S10 is greater than or equal to 15. So facts about Poisson is that the expectation and variance are both mu, so the expectation of S10 is 10, and the variance of S10 is 10. And so here's a picture of Poisson with mu is 1, and the Poisson with mu is 10, which is the S10, and we see that S10 looks approximately normal. What CLT says is that S10 is approximately normal, mean 10, variance 10. And you can then find the probability that S10 is greater than 15 just by using this normal approximation involving the CDF phi. Okay, so have a great weekend, and I'll see you next week.